In this video, we're going to talk about quantifiers. So coming back to the example we talked about earlier, all men are mortal. That uses a quantifier. The quantifier is the word all, that it's applying to every man. Another quantifier is like the word some. Some cats do not have fur because there are some cats who are furless. Okay, so those two words, all or some, kind of become the basis of the two most important quantifiers. So for all, we use the symbol that looks like an upside down capital A. All right. There exists looks like a backwards capital E. So those two symbols are going to mean to us for all and there exists. There are other ways of saying that, and we'll look at that as we kind of go through this. But for right now, we're kind of just starting there. So let's look at this right below here. We write for all x and there exists x. So this asserts this statement here, for all x, p of x, it asserts that p of x is true for every x in the domain. So whatever the domain is, it's going to be true for all of them. When we use the there exists implies that it's true for some of the x. And by some, it actually could just be one. All right. One would count as some. All right. Let's look at some examples. Let's say if p of x is bigger than 0. Okay. And u is the integers, then to say for all x, p of x, that is not a true statement. This is false. Because we're saying that this statement here, that x is bigger than 0, is true for every integer. And that's not true. There are negative integers, so that's completely untrue. However, if they change the domain and they say then it's positive integers, well, this would be true for every integer. All right. If p of x is even, and we're talking about the integers, since they're using the for all notation, that would be false because there are some integers that are odd. You could also read it as for some when you're looking at the there exists. Or another way of saying it is there exists an x such that p of x. So in other words, there's at least one example that, holds that this is true. And the next one says that as well. So basically, there are different ways of saying that if you want to kind of look at the different versions of how to word that. Okay, so let's look at some more examples here. If p of x denotes x is bigger than 0 and u is the integers, now they're switching to the there exists notation, or there is some x such that this is true, this would work, right? Because some of the integers are bigger than 0, okay? In this case, when we say when x is less than 0 and u is positive integers, well, that doesn't work because there's absolutely no positive integers that are going to be less than 0. So this is going to come out false. Even though they're using there's just one that works, there isn't a single one that's going to work there. P of x denotes x is even and u is the integers. Okay, now this would work because there exists some integers that are even. So this is true. All right. So we have to just kind of plug in what this means. There exists, or there is some, and this one is for all or for every. It's a way of saying both of those. Okay, real quick, there is a special quantifier that does happen, and it's this exclamation mark. See this little exclamation mark right there? That exclamation mark means it's only true for one value. Only one value works. So here, an example down here is if p of x denotes x plus 1 equals 0. There's only one solution that works, okay? X has to be -1. That's the only one that works. then there exists only one X where this is true. Okay, so that's just a bonus. I'm not going to really assign homework on that, but it is something you might see in the future when you're writing arguments and there's only one case that does in fact work. Okay. So this example, I kind of went through, I answered it for us, and we'll fill in a little bit for you. Okay, so let's say that when the domain is finite, okay, when we're looking at a set of numbers and we'll be able to get through them, okay, then we can look at the loop and say, all right, so if every value that we look at, P of X is true, then we could say that for all X, P of X is true. So like if we step through all the numbers, okay, so if U happens to be 1, 2, and 3, and we go through and we look at P of 1, P of 2, and P of 3, and we're like, yep, they're all true, then that means that for all X, P of X is true. But if we step through them and we hit one that comes out false, okay, then this statement for all X, P of X is false, and we don't have to keep testing. So we terminate the loop. So that's kind of using, let me zoom in a little bit, sorry. That's kind of using computer science wording there, the idea that we'll terminate the loop. Okay, we'll stop testing because there's no reason to test any further. We found one that didn't work. Okay, so for there exists, that works a little bit differently. So if at some step it comes out true, then you can say there exists X, P of X is true. But if you go through all of them and you don't find one that's true, then there exists X such that P of X is not true or is false. It's a false statement. And we can do this for infinite domains, but we don't actually terminate the loops in some cases because you're going to keep testing forever. That's not pleasant. Okay, let's go ahead and talk about properties of quantifiers. So the truth value of there exists X of P of X, and for all X, P of X depend upon both the propositional function and the domain. So both of those come into being true or false. So let me give you an example. Let's say P of X is the statement X is less than 2. And let's say U is the statement positive integers. Okay. In this case, this statement for all X, P of X is not going to be true. This is going to come out false because since we're talking about positive integers, this only works for some of them, right? And the other half of them, it's not going to work. They're going to be bigger than that number. All right. So in this case, there exists X, P of X. Well, this is going to be true. So this one does come out true in this case. All right. So it depends. If I change that a little bit, it's possible that the false and true will change based on which one I decide to change. Okay. So like, for instance, if I say, instead of U being positive integers, if I made U negative integers, well, that changes it because now this does become true because every negative integer is smaller than 2. And so does the other one. That's true also because there is some in there that do work. So happens to be all of them, but some of them work. So it does matter how you state for the propositional function and the domain. Both of them have to be kind of included. Okay, so the precedents of the for all and there exists are that they end up having higher precedence when you're looking at statements. Okay, so for example, if I just wrote this, for all X, x, p of x, or q of x. Okay, what that means is, first thing I have to tackle if I'm looking at whether or not this is true is I actually have to tackle this part right here. So really, if I'm giving priority, it would be thinking of it in parentheses. So this is what I would look at first. Is this statement true for all x, p of x? The proposition for p of x is true, okay? And then if once I've determined all of those, I would look at combining that with q of x, okay? But often people really wanted to write for all x, p of x, or q of x. In other words, they actually meant to look at the or statement first and then see if it works for all of them. Okay, so this does not equal the statement above, because without indicating with the parentheses, we assume that the for all x applies to the first proposition only. Otherwise, you do have to use parentheses to indicate that it's applying to both of the propositions. Okay. Okay, so hopefully that makes sense. Now, as we kind of go through some examples, it might help make more sense. Okay, so let's do some translating. Let's translate this into predicate logic. Every student in this class has a course in Java. Okay, there's a couple ways to do this. The first way, or I should say the biggest thing you have to decide is what the domain is, okay? So when you make you, let's say, students in the class. So if we make you students in the class, then we need to create a propositional function, okay? So students in the class, so we're interested in them taking a course in Java. So then let's say J of X is taking a course in Java. Okay, so to translate this, we would say for all X, J of X, every student in the class takes a course in Java. That's how we would say this. So that's the first way we could do it. But there is another way, an alternative way. If we decided to let you be everyone, all people, that changes things, because now not only do we have to weed out people who take a course in Java, we have to weed out people who are in the class. Okay, so we still have, I thought I was running out of room, J of X. I'm just going to shorten the statement for the sake of space. Okay, so J of X is Java. But we'll also need to include S of X, where S of X is a student in the class. So now we have to say that people who are in the class, or who take this class, students in the class, then we know they are taking Java. And since this is true for all of them, I need to put for all X in the front and parentheses, because I need to apply, the for all X needs to apply to both propositions. Okay. So there's the two ways that you could do it. And it depends on how you define you. Clearly, defining you the first way is simpler. It allows us to do a simpler statement. Okay. Okay, so let's try another one. Some student in this class has taken Java. So again, it depends on how we define you. Let's use, we'll use the same J of X and S of X. Okay, so from above, J of X is taking Java, S of X is a student in the class. and I'm writing it easily. Okay, so let's see. Let's assume U is students in the class. That means then all we have to say is some student, or there exists a student that has taken Java, and this is assuming students from our class. Or if we make you all people, then we have to say, then we have to say that there exists someone that is a student in the class and they have taken Java. So notice I switched away from the then statement, right? I'm saying and in this case, okay? And so they're both a student in the class and they have taken Java. So it's not that one is implying the other. Whereas up here, being in the class was implying they took a course in Java. That's why I used the implication symbol, the if-then statement, okay? But down here, we're saying that they're in the class and they've taken a course in Java. Different kind of way of looking at that. Okay. My computer is kind of upset that I keep moving the screen. Give me a second. There we go. Okay, so let's look at negating quantified expressions. Okay, so this does get a tiny bit more complicated in terms of what negating does when you're talking about for all versus some. It's not that complicated, but it can be a little if English is not your first language. Okay, so be aware. When you say every student in your class has taken a course in Java, okay, then the negating of that is to say it is not the case that every student in your class has taken Java, right? But a better way of saying that is to say that there is a student in the class who hasn't taken Java. Okay, so to say that to negate this is to say that basically it's not the case that every student in the class has taken Java, but really what that implies is there's at least one student in there who hasn't taken Java. All right, so symbolically we are saying that for all x, j of x is equivalent, remember that symbol for equivalent that we learned in the last section, to saying that there exists an x such that this doesn't happen. So when you say all the students in the class have taken Java, we're saying there exists some student who hasn't taken Java. That's what that says. Okay, so let's do this ourselves. So let's consider there is a student in this class who has taken a course in Java. All right. So the negation is not the case that there is a student in this class who has taken Java. All right. So what we're saying in that case is that every student in the class has not taken Java. Or another way of saying that is no one has taken Java in the class has taken Java. Okay, so symbolically, that's saying there exists j of x, there exists someone who's taken Java, is equivalent to saying that everybody has not taken Java. These two are equivalent statements. Oh, I'm sorry. I keep forgetting to put the negation in front. Oh, I'm so sorry. That probably was confusing up here. I forgot the negation. Oh, there is a negation. I'm so sorry. That was probably very confusing. I apologize. So negating this statement, saying that there it is not the case that everyone has taken Java, is the same thing as saying there exists someone who hasn't taken Java. Down here, to say that there is someone who hasn't taken Java in the class, or I'm sorry, that there doesn't exist someone who has taken Java in the class, is to say that everyone in the class has not taken Java. Okay, I'm so sorry. I meant to put the negation symbol. That changes things. I'm so sorry. Okay, let's look at De Morgan's laws for quantifiers. Okay, so De Morgan, we talked about that also in the last section. All right. Is the idea of remember I kind of said it's almost like a distribution. Okay. So let's step through this. Based on what we just talked about, the logically equivalent argument to this negation is for all x not p of x. All right. So when is the negation true? So this negation is true. It's saying it's true for all x when p of x is false. So for every x, p of x is false. Wow, I'm writing so small. I'm sorry. Let me zoom in a little bit. For every x, p of x is false. When is the negation false? It's false when there is x for which p of x is true. Okay, so the equivalent statement here is there exists an x where this is not true. So this happens is there exists or there is an x where p of x is false. That's when this whole thing is true. It's not true when p of x is true for every x or for all x. Okay. So what the reasoning shows is what I said up above, that the negation statements for all x, p of x is equivalent to there exists x, not p of x. So in other words, this is De Morgan's law, what we stated above. There exists x, p of x for all x, not p of x. All right. Let's do some more translating, some more practice with this. Okay, so let's see. Translate from English into logic. Some student in this class has visited Mexico. Okay, so I want to say, again, it depends on how you decide to assign you. All right. We can assign you to be students in the class. Oops, students in the class. And we have to make this statement. Otherwise, it doesn't make sense. Okay. So in this case, if that's you, then when we say some student in this class has visited Mexico, I need to then create the proposition. So m of x is visited Mexico. Okay. Then we could say that there exists x such that m of x, such that that person has visited Mexico. So someone in the class has gone to Mexico. Okay. Here, we need to add another proposition. We're going to still use m of x from above, but now let's do c of x is visited Canada. Okay, now this is different. So now we're looking at, oh, it helps if you put the right spelling. Canada, there we go. In this case, it's that they've gone to Canada or Mexico. Okay, Canada or Mexico. So every student in this class has visited Canada or Mexico. So the way we would state this is for all x, c of x or m of x. And putting the parentheses around that because we want this to apply for all x when both of these. Okay. All right. Okay, so this is an example that they did with funny made up words. Okay, so don't get hung up on that. They're defining our domain to be flegals, snurds, and thingamabobs. They were kind of being cute about it. Okay, so let's translate the following based on given this U and these propositions. Okay, so let's translate everything is a flegal. That would be for all x, f of x. Okay. Nothing is a snurd. Okay, so nothing is a snurd. So we could say that a couple different ways. I like to, because it says nothing, I start to think the for all, right? I think nothing, none of these people. So for everybody, none of them is a snurd. That's one way of saying it. But you could also say, or there doesn't exist someone that is a snurd. That's another way of saying it. Okay. All flegals are snurds. So this is saying that flegals, being a flegal means you're a snurd. And this is true for all x, and we want to put parentheses around it. So we're saying that for all of them, this is true. Okay. Some flegals are thingamabobs. Excuse me. So there are some flegals out there that are thingamabobs. Now, because it says some, there exists people who are members of flegals and thingamabobs. That was T. Yeah, T of X. And we would want to do it both. So here's what we're really saying. And I like to refer to set notation for statements like this. In this statement, we're saying that there are people who are both flegals and thingamabobs. In other words, they're these people here. They're in both groups. So it's not saying that all flegals are thingamabobs. All flegals are thingamabobs, or like here, all flegals are snurds. That looks like this. That means that here are the flegals, and then the snurds are actually inside, because everybody in the group of snurds is in the group of flegals. That's what this statement says here. Okay, all of them. Oops, I'm so sorry. I thought I selected the highlighter. I did select the highlighter. Okay, it still doesn't see it. I'm so sorry. It like tricked me into thinking it was selected. So this statement ends up looking like one set embedded inside the other one set within the other one. Whereas in this statement, when we're saying that some of them happen to be thingamabobs, that ends up looking like this kind of picture here, where there's an overlap between the two groups. No snurd is a thingamabob. Okay, using my logic here, I'm just going to draw it one more time since I'm kind of on the path to drawing these. In this case, none of them overlap. So here's the snurds, here's the thingamabobs. They're completely separate. Okay, they're apart from each other. And how we would do that is to say that they're separate, to say that they don't share anything in common, is to say they don't share anything in common. You could say for all x, I'm sorry, that sounded bad. For all x being a snurd, or I should say not being a snurd, or not being a thingamabob. So for everybody, that would be the case. They're either not a snurd or not a thingamabob. Another way of saying that is there exists someone, I'm sorry, there doesn't exist someone that is both a snurd and a thingamabob. Ooh, I like this one better. I like that one better. There doesn't exist someone, right, that that is a snurd and thingamabob. I like that one a lot better. Okay, If any flegel is a snurd, then it is also a thingamabob. Okay, they use the if-then statement there. So we definitely have an if-then, but that only happens when we're looking at flegels that are snurds. So we're only looking at flegels that happen to be a snurd as well. So both of those, flegels and snurds, so if both of those are true, they're both a flegel and a snurd, then they're a thingamabob. And we would put the for all on the outside.